In this presentation, I'll be explaining what is the concept of comparators, what are the few applications of the comparators. Coming to comparator, a comparator is a circuit which compares the input voltage applied to one input of op-amp with a known reference voltage at the other input of the terminal. Therefore, for example, here this is an op-amp. In comparator operation, op-amp, there is no feedback path here as such. Therefore, to the non-inverting input, you are giving a signal, and you can give the inverting terminal. Either you can give a positive voltage or a ground voltage or negative voltage, whatever it is, and compared to this, whatever the voltage you are applying to this terminal, we are compare this. How much is this voltage? Based on that one, there will be an output voltage. As an example here, during positive half cycle, this voltage is more than the ground voltage. Then the output voltage is equal to whatever this plus here, plus Vsat and minus Vsat, and this output voltage is equal to plus Vsat. During the negative half cycle of the input here, since this voltage is less than this voltage, that is because the ground voltage, here you are getting a less voltage. That is why the output voltage is equal to minus Vsat. Then the output is changing to minus Vsat. Or basically the input voltage to the one of the input to the op-amp is being compared with other input voltage. Based on that one, you will be getting a output voltage either plus Vsat or minus Vsat, and there is no feedback path for this comparator. And comparator can be classified into two types. One we call it as a non-inverting comparator. Second one we call it as an inverting comparator. In non-inverting comparator, you are giving the input to the non-inverting terminal. This is a non-inverting comparator. And instead of that one, if you are giving this to the inverting input, that we call it as inverting comparator. Now let us see first a non-inverting comparator. A non-inverting comparator, that is, you are giving the input to the non-inverting input. This is the input signal that is given to the non-inverting input. This reference signal what you have to compare, that can be either positive or negative or zero voltage. Now in this case, we are comparing with a positive reference voltage. We are applying a positive reference voltage here, and we are comparing the input voltage that is applied to the non-inverting terminal here. Therefore, the voltage applied to the non-inverting terminal is this one. This is the voltage that is being applied to the non-inverting terminal plus input terminal. And this voltage is being compared with the voltage that is applied to the inverting terminal, because we are applying a positive reference voltage. This is the voltage that is being compared with that one. Therefore, this is the positive reference voltage and this is the input voltage. And output, that is the output of op-amp. There is no feedback as such in a comparator. And the output feedback, the output is equal to V0 equal to plus Vsat if Vi is more than V reference. If Vi is more than V reference, V0 equal to V out equal to Vsat. Therefore, if V input voltage is more than V reference voltage, output voltage equal to plus Vsat. Now, if input voltage Vi is less than the reference voltage here, the output voltage equal to minus Vsat. Therefore, this is the rule that is to be obeyed in this case when we are applying to the non-inverting input as well as a positive reference voltage. And here, this is for a non-inverting input voltage. This is the rule to be applied here. If Vi is more than V reference, output voltage equal to plus Vsat. If Vi is less than V reference, output voltage equal to minus Vsat. Applying this theorem to here, you can see that one. Therefore, from this point to until this point, if you see that from 0 to until this point, we can see that input voltage is less than the reference voltage. When input voltage is less than reference voltage, output voltage equal to minus Vsat. That is why until this point, you will be getting a output voltage equal to minus Vsat. Now, after this point, you can see that one input voltage is more than the reference voltage. Reference voltage equal to certain voltage, that is V reference. Since the input voltage is more than the reference voltage, output voltage equal to plus Vsat. That is why from here to here, you will be getting a plus Vsat. Then again, from here to here, you can say that one input voltage is less than the reference voltage. Input voltage is less than reference, output voltage equal to minus Vsat. That is why we are getting a minus Vsat. Therefore, this is the output voltage of this comparator, which is a non-inverting comparator with a positive reference voltage. And this is when Vi is more than V reference, output voltage equal plus Vsat. When Vi is less than V reference, output voltage equal to minus Vsat. This is the rule to be followed in the case of a non-inverting comparator. Therefore, the output voltage will be either plus Vsat or minus Vsat, depending upon the relative value of the input voltage as well as the reference voltage. Now, the same non-inverting comparator in which you are giving a negative reference voltage. Previously, we have seen a positive reference voltage, but here you are giving a negative reference voltage. Minus terminal is there. That is given. Now, let us see. In that case, the rule is that one. If input voltage is more than the reference voltage, output voltage equal to minus Vsat. If input voltage V in is less than V reference, output voltage equal to minus V. Just to remember that one, you can see that one. If input voltage is, if this voltage is more than reference voltage, I mean in this case, more here same thing. I mean a non-inverting, this is a non-inverting comparator with a negative reference voltage. Same thing here. When input voltage is more than V reference voltage, output voltage equal to plus Vsat. And if input voltage is less than V reference, output voltage equal to minus Vsat. What I want to explain, that is for a previously I told you, that is for a inverting comparator. For a non-inverting comparator, this is a rule, same as the previous one. If input voltage is more than reference voltage, output voltage equal to plus Vsat. If input voltage is less than V reference, output voltage equal to minus. Applying to this one, this is the input voltage and this is the reference voltage. When input voltage is more than reference voltage, you can see that one output voltage plus Vsat. That is why we are getting a plus Vsat until this point. And from here to here, if you see that one, input voltage is less than the reference voltage. If input voltage is less than reference voltage, output voltage equal to minus Vsat. Therefore, you are getting a minus Vsat. That is the whatever the voltage applied to here, minus Vsat, biasing voltage, minus Vsat is that. Therefore, based on this magnitude of this reference voltage, which is a negative value, the output voltage will be either plus Vsat or minus Vsat. If input voltage is more than V reference, output voltage plus Vsat. If input voltage is less than V reference or reference voltage, output voltage equal to minus Vsat. Therefore, this is for a non-inverting comparator with a negative reference voltage. Therefore, this rule is common for a either with a positive reference or a negative reference for a non-inverting comparator. Previously, we have seen a non-inverting comparator. In this one, we are going to consider an inverting comparator in which the input signal is applied to the inverting input. Previously, here we applied. But in this case, we are applying the input signal at the inverting input and the reference signal is applied to the non-inverting input. Here also there are two cases with a positive reference voltage and with a negative reference voltage. In that case, the rule is just reverse of the previous one. If input voltage is more than reference voltage, output voltage equal to minus Vsat. If input voltage is less than reference voltage, output voltage equal to plus Vsat. Therefore, just reverse of the previous one. In the case of inverting comparator, now let us see with a positive reference voltage. Therefore, we are giving the input to the negative input and the reference voltage is given to the positive terminal. And here with a positive voltage, positive reference voltage. Therefore, this is the input voltage and this is the positive reference voltage. Now let us apply this one. This thumb rule you apply. If until this point we can see that one input voltage is less than the reference voltage. Input voltage is less than reference voltage. Output voltage equal to plus Vsat. Output voltage. That is why you are getting a plus Vsat here. Now from here to here you can say that input voltage is more than the reference voltage. Since input voltage is more than reference voltage, output voltage equal to minus Vsat. That is why here during this period from here to here you will be getting minus Vsat. Then from here to here again the input voltage is less than the reference voltage. If input voltage is less than reference voltage, you can see the output voltage equal to plus Vsat. That is why from here, from this point, again the output is changing to plus Vsat. Therefore, this is the output voltage for a inverting comparator with a positive reference voltage. Therefore, the thumb rule is that, just to remember that one, if input in this case, in the case of inverting comparator, if input is more than reference voltage, output equal to plus minus Vsat. And if input voltage is less than V reference, output voltage equal to plus Vsat. And the previous one for a non-inverting comparator is just opposite to this one. Just to remember that one. Now continuing the inverting comparator with a negative reference voltage. Again, inverting comparator means you are applying the signals to the inverting signal. This is the input signal that is applied to the inverting. Therefore, basically in comparator, you are comparing these two magnitude of these voltages, in which the input signal is given to the negative input of, that is why it's called inverting comparator, and to the non-inverting, that is the reference voltage. It can be either positive or negative. previous slide we have seen it is a positive voltage, but in this case you are applying a negative voltage, negative V reference. Again, that rule is the same. If input voltage is more than reference voltage, output voltage equal to minus V sat. If input voltage is less than V reference voltage, output voltage equal to plus V sat. Therefore, applying the same thing rule here, this is the input voltage and the reference voltage equal to negative reference voltage you are applying. Since from here to here, you can say that input voltage is more than the reference voltage, then output voltage equal to minus V sat. That is why you are getting a minus V sat. And from here to here, you can see that one input voltage is less than the reference voltage. Since input voltage is less than reference voltage, output voltage is equal to, we can say it is equal to plus V sat. That is why here you are changing to plus V sat. Therefore, only thing is that you are applying this thumb rule to find out either plus V sat or minus V sat depending upon the magnitude of the input voltage signal as well as the reference signal. Therefore, this is an inverting comparator. Since we are giving the input at the inverting point, it is called an inverting comparator, in which that is being compared with a negative reference voltage. And the rule is that if input voltage is more than the reference voltage, output voltage equal to minus V sat. And if input voltage is less than the reference voltage, output voltage equal to plus V sat. This is for an inverting comparator. But for a non-inverting comparator, it will be just reverse. That is, if input voltage is more than V reference, output voltage equal to plus V sat. And if input voltage is less than V reference, output voltage equal to minus V. Just opposite to that one. Or you just remember that one. And based on this rule, you can find out whether it is plus V sat or minus V sat depending upon the relative magnitude of the input voltage as well as the reference voltage. That is the inverting comparator with a negative reference voltage. Next one is a zero crossing detector, ZZD we call it. This is widely using op-amp configuration, comparator configuration, which is an application of the comparator. Therefore, when in that one, in zero crossing detector, one of the input will be grounded and the input will be given to other, signal will be given to other input. Therefore, depending upon the signal, that is whether it is giving to plus input or minus input, they are classified as non-inverting ZCD as well as inverting ZCD. Therefore, when one input of the comparator is connected to the ground, it is known as zero crossing detector, ZZD. Therefore, one of the input point of the comparator is being grounded, and then we call it as zero crossing detector. And because the output changes when input changes at this zero voltage, that's why it is changing the change either from plus V sat to minus V sat or minus V sat to plus V sat. That transition is taking place at zero voltage. That is why it is called zero crossing detector. Now, depending upon the voltage that you are applying either to the plus input or minus input, they are classified as non-inverting zero crossing detector and inverting zero crossing detector. Coming to the non-inverting zero crossing detector, you are giving the input signal to the non-inverting input and the inverting input is grounded. And in this case, same rule you can apply that one. In the case of a non-inverting zero crossing detector, non-inverting comparator configuration only. If Vi is more than V reference, this is equal to plus V sat. If Vi is less than V reference, this is equal to minus V sat. Therefore, same thing if you apply here, you can say that one during the positive half cycle, you will be getting a plus V sat, and during the negative half cycle of the positive half cycle of the input, you will be getting plus V sat, and during the negative half cycle of that one, you will be getting minus V sat. Or this waveform, this is an input waveform that is applied to the non-inverting terminal, that is converted to a square waveform, and in which the transition is being taken place at the zero crossing point. That is why it is called zero crossing detector. Or you are converting a sinusoidal signal into a square waveform. That is done by zero crossing detector. This is a non-inverting zero crossing detector. In an inverting zero crossing detector, the change is that rather than giving the input to the non-inverting terminal, here the input is given to the inverting terminal. The signal that is going to be to the detector, zero crossing detector to be done for that one, that is given to the inverting terminal, and non-inverting terminal is grounded. Therefore, again the rule is that in a case of a non-inverting comparator, rule is that if Vi is more than V sat, V0 equal to minus V sat. If Vi is less than V sat, output voltage equal to plus V sat. Same rule here. And when Vi is more than V reference is a 0, then output will become minus V sat. That is why during that period you are getting minus V sat. Now, when Vi is less than V reference, output voltage is equal to plus V sat. You will be getting a plus V sat. Therefore, this is the Actually, this is the inverted version of this one. This is the score waveform corresponding to an input of sinusoidal which is applied to the inverting terminal. You will be getting an output of this one. Again, the transition is being taken place at the zero crossing points. That is why this is called a zero crossing detector. Therefore, there are two types of zero crossing detector: non-inverting zero crossing detector and inverting zero crossing detector, in which the input signal is being compared with a zero reference voltage. This is another application of a op-amp comparator configuration it is widely using, that is called Schmitt Trigger. Schmitt Trigger, also it is called a regenerative comparator. Schmitt Trigger or regenerative comparator, in which we are from the output, that is, this is the input to this. We are giving the input to the non-inverting terminal. Sorry, inverting terminal. We are giving an input to the inverting terminal through a resistance, and to the non-inverting terminal, the plus terminal. Let's say positive feedback. Output is taken through a two resistors R1 and R2, and that is fed back to the positive terminal. Of course, there is a reference voltage is applied to, rather than grounding this one, you can control this the magnitude, so that this magnitude can be controlled. In order to control that one, rather than connecting a ground voltage, you are applying a reference voltage, V reference. So this is a circuit diagram of a Schmitt Trigger regenerative comparator, in which as you compare, as you know that one, the gain with feedback equation is given by gain, open loop gain divided by 1 plus or minus open loop gain into beta. This is a basic equation of a closed loop gain, and if it is a negative feedback, it will become plus sign, and if it is a positive feedback, this will become minus. Therefore, for a positive feedback circuit, this is a positive feedback circuit, the gain equation is given by, that is, gain with feedback AVF equal to open loop gain divided by 1 minus open loop gain into beta, 1 minus AOL into beta. Therefore, this is the basic equation of the closed loop gain of this Schmitt Trigger. Now, this product, this is called the loop gain. The product AOL into beta, that is called the loop gain, and that is adjusted to, in order to get a operation as a regenerative comparator or a Schmitt Trigger, or this is being adjusted to the magnitude of AOL and beta is adjusted to unity. In that case, we can see that when the gain is infinity, 1 minus 1, it is equal to infinity. Thus, results an abrupt transition from either to plus V sat to minus V sat and minus V sat to plus. That abrupt transmission can be obtained. That is done by making a closed loop gain into beta. Beta is called a feedback factor. This feedback factor is beta, means feedback factor, which is equal to R2 divided by R1 plus R2 in this case, which is grounded, and that product of AOL into beta, that if you make it equal to unity, then that will be resulting the gain of infinity, or an abrupt transition between extreme values of plus V sat and minus V sat will be taking place. Therefore, in practical circuits, rather than making AOL into beta exactly unity, it is made slightly more than 1. Therefore, the loop gain AOL into beta, open loop gain into the feedback factor beta, that loop gain is exact, rather than keeping exact unity for a long time, and because of the variation of the temperature temperature variation as well as the voltage variation, that is why always we will be keeping this value AOL into beta will be kept as greater than unity in most of the applications. Now, continuing the smooth that already we have seen, this is a Schmitt Trigger circuit or regenerative circuit, in which here input voltage is supplied, and here is the reference voltage, and here the output voltage will be getting. This is a feedback circuit in which the gain is feedback beta is given by R2 divided by R1 plus R2, and the circuit can exhibit a phenomena called hysteresis. We'll be seeing what is that hysteresis. And here, if you see, consider here, the input is given to the inverting, whatever the signal, that signal input signal that is given to the negative terminal through a resistance R1, therefore through the op-amp inverting terminal, and the feedback signal is applied to the, that is the feedback signal, that is from the output is taken, this one, that is applied to the positive input of that one, and the input voltage, that is Vi, triggers the output V0 every time when it exceeds, that is when input voltage exceeds a certain voltage levels, that is output, when this voltage
once this voltage is exceeding certain voltage here, the output will be translating from plus Vsat to minus Vsat. Now let us analyze this one as these voltages levels are called, there are two voltage levels, like what we call it as upper threshold voltage and one is called the lower threshold voltage. As you considering this one, assume that this is the input voltage, this is the sinusoidal one is the input voltage, and there will be two voltages that will be defining as upper, this is called the upper threshold voltage. I am defining that as upper threshold voltage, and this is the lower threshold voltage, meaning that if the input voltage is going more than upper threshold voltage at this instant here, in this case, since you are giving a negative input at this kind, here the output voltage be changing to minus Vsat. Therefore, here the output voltage is changing to minus Vsat. Then again, if the input voltage is going less than the V reference, is not like that one, not less than the upper threshold. Next transition is taking place when the input voltage is less than the lower threshold limit, that is VLT, that is this voltage. Then again that output is changing from minus Vsat to plus Vsat. Again that will be continuing. Again the transition from low to high, that is from the transition from low to high is taking place when the input voltage is less than the lower threshold voltage, and the transition from high to low is taking place when the input voltage is more than upper threshold voltage. Therefore there is a delay, there is a delay like that, there is what is called the hysteresis delay is there. That is the difference of upper threshold voltage minus lower threshold voltage. That is called the hysteresis width, that is VUT minus VLT, that is called the hysteresis width. Therefore, these voltage levels are called upper threshold voltage. This is the upper threshold voltage and this is the lower threshold voltage, and the difference between these two are called the hysteresis width. Therefore, when the input voltage is going more than the upper threshold voltage, output is changing from plus Vsat to minus Vsat, and again when the input voltage is going less than the lower threshold voltage, again the output is changing from minus Vsat to plus Vsat. Therefore, this is the output voltage available at this one, and this is the input voltage, and this is the upper threshold voltage, and this is the lower threshold voltage, and the difference between that one is called it as hysteresis width. Continuing the Schmitt Trigger operation here, as I already seen that I told you, there are two voltage limit like upper threshold voltage and lower threshold voltage, and the difference of that one we call it as hysteresis width. Now coming to the, you have to calculate what is VUT and what you have to design what is VUT and what is VLT. Based on that, you have to find out these values of this one, R1, R2, etc. Therefore, you have to calculate what is the upper threshold voltage and what is the lower threshold voltage. First, assume that this voltage can be either plus Vsat or minus Vsat. First, I am assuming that this voltage equal to plus Vsat. If this voltage equal to plus Vsat, that is, if output is plus Vsat, now what is the voltage coming at this? Because here you are applying a reference voltage. Therefore, there are two inputs. One, if you see that one, here equal to plus Vsat and here it is equal to reference voltage. Now, what is this voltage question? That you can have to apply the superposition theorem. When V plus Vsat is present, you have to ground this one and then you have to see what is this voltage. Then when V reference is present, you have to ground this one and then you have to see what is the voltage. When both are present, it is the summation of these two. That is what we call the superposition theorem. And like that one, we can see that suppose the output voltage equal to plus Vsat, the voltage at plus point, the voltage at this point, input terminal can be found out by or can be obtained by superposition theorem, as I already told you. That is voltage at plus input terminal. When plus Vsat is present, this voltage is given by Vsat divided by R1 plus R2 into R2, R1 plus R2 into R2. Then when this is present, reference voltage is present, it is equal to V reference divided by R1 plus R2 into R1, because this is a grounded, into R1. Therefore, this is the voltage that is defined as upper threshold voltage VUT. That is, this is referred as upper threshold voltage VUT. Meaning that as long as the input voltage is less than the upper threshold voltage, the output will be remaining constant at plus Vsat. That is, if the input voltage is just crosses or greater than the upper threshold voltage, output voltage switches into the minus Vsat and remains at this level as long as the input voltage is more than as long as actually this voltage is more than lower threshold limit. Actually, it's a lower threshold voltage. Let us see what is that. Now there is another term when, as I told you, when this voltage is coming more than the upper threshold voltage, here this voltage will be changing to minus Vsat. As if Vi is greater than V out voltage, that will be changing to minus Vsat. Once the voltage at this point is changing to minus Vsat, again you have to calculate what is the voltage coming at this terminal. Then that is equal to, that is voltage at the, that is when input voltage equal to minus Vsat, voltage at plus input terminal can be found of superposition theorem, and voltage at the plus terminal is given by minus Vsat divided by R1 plus R2 into R2 plus V reference divided by R1 plus R2 into R1. Same as, only thing is that it will minus Vsat comes. And this equation that is representing the lower threshold limit VLT. For VLT is given by this one and upper threshold voltage that is given by this one. The difference of this VUT minus VLT that we call as a hysteresis with VH. That is a VH.
Continuing the Schmitt Trigger circuit in this one, and here we have found out what is the upper threshold voltage in terms of these resistance values and saturation voltage as well as reference voltage. Upper threshold voltage is given by Vsat into R2 divided by R1 plus R2 plus V reference voltage into R1 divided by R1 plus R2. This is upper threshold voltage. And lower threshold voltage means when the voltage of minus Vsat comes here, the corresponding voltage, what is the voltage coming at this point, which is equal to minus Vsat into minus Vsat divided by R1 plus R2 into R2 plus reference voltage V reference divided by R1 plus R2 into R1. This is the lower threshold voltage. And the difference of this one we call it as hysteresis voltage, which is equal to V upper threshold VUT minus VLT. Difference of this one you will be getting twice into the reference voltage into R2 divided by R1 plus R2. This is the hysteresis voltage. That is, here the input is changing at this, and here it is not changing at this one. Instead of that one, it is changing at this point only. Therefore, there is a hysteresis taking place. And how much is that hysteresis? Is the difference of these voltages, that is VUT minus VLT. Just like this one. This is the, in one direction it is changing. Here, if you the input is changing, here more than that, it is changing to minus. Again, it is not changing here. Rather than it changes only at this point. Therefore, a hysteresis is taking place. That is because of this difference in voltage of upper threshold voltage and difference lower threshold voltage that is given by this equation. And if the input voltage cools less than the lower threshold voltage, that is the output voltage changes from, which is equal to changes minus Vsat to plus Vsat. That's already we explained. That is here if the input voltage is changing going less than the lower threshold voltage, the output voltage is changing from minus Vsat to plus Vsat. Again, this change is when input voltage is going more than upper threshold voltage. Therefore, this is the output voltage, and the hysteresis voltage is this one. Therefore, this is a Schmitt trigger which is widely using, that is obtaining using the op-amp circuit. Now, continuing the Schmitt trigger here, already we derived what is the VUT and VLT. Now, if you are keeping the references, a certain case, if you are keeping the reference voltage to 0 voltage, ground voltage, now what is happening? If this is kept ground voltage, this quantity will become 0 and this quantity will become 0. Meaning that upper threshold voltage is equal to minus of lower threshold voltage. VUT equal to minus VLT. For example, if VUT equal to say 5 volt, VLT equal to minus 5 volt. As an example here, this is the input voltage, and VUT you are getting a plus voltage, some value of plus voltage, and the VLT will become minus, magnitude is same but negative side, minus of that one. Therefore, that in that case, if you compare this one, if input voltage is more than VUT, the output will be changing from plus Vsat to minus Vsat, that is changing. Again, when the input voltage is going less than the lower threshold voltage, output is changing from again plus Vsat, sorry, minus Vsat to the plus Vsat. Then you are converting this this sine wave into a square waveform, making the reference voltage equal to 0. Therefore, if we select the, if we select, if you select, meaning that if you select the upper threshold voltage is same as magnitude of lower threshold, put a negative sign, VUT equal to minus VLT, a symmetrical square wave is obtained at the output of the Schmitt trigger. That is what is happening here. That is can be observed from this one. That is output is, and if the, in this case, the point at which it is transition is being taking place, this angle, that will be happening when Vm sin theta, that is, this is the input voltage equal to Vm sin theta, when that is equal to the upper threshold voltage, or sin theta equal to the upper threshold voltage divided by the maximum voltage of this. So this, from this one you can find out what is the theta at which that is changing, at what instant the transition from plus Vsat to minus Vsat, or from minus Vsat to plus Vsat is occurring. That can be calculated by comparing this magnitude of the sinusoidal with the either upper threshold voltage or lower threshold voltage. Coming to a problem on Schmitt trigger. Now the Schmitt trigger circuit is that, it is of course one point to be remembered is that in this circuit you are giving the input to the negative input. You can have even positive also, but in this here it is you are, the input is given to the negative and the feedback is positive. That is why we are giving input to the negative. Therefore, in a Schmitt trigger circuit shown here, R1 equal to 50 kilo ohms. Sorry, R1 equal to 50. This is R1. R1 equal to 50 kilo ohms, and R2 equal to 100 ohms. That is the R2 equal to 100 ohms. And the reference voltage, instead of applying any voltage, this is grounded. Reference voltage is grounded. And the input voltage is equal to 1 volt peak to peak sinusoidal. Here the signal is applying a sinusoidal signal with the peak to peak value equal to 1, or 0.5 is the maximum value, 0.5 sin omega t. That is the input voltage at this point. And the saturation voltage will be either plus 14 or minus 14. That is plus Vsat and minus Vsat. And the threshold voltage. And you have to calculate what is the upper threshold voltage and what is the lower threshold voltage. Since one thing is that, since reference voltage, you can write the equation for the VUT and VLT. That is already we derived that equation. And in that case, since both are in this case, and wave and once and since what is that, V reference is made 0. Since V reference is made 0, this will be 0, or VUT will be equal to minus VLT, and that is equal to VUT equal to minus VLT, which is equal to, that is equal to Vsat plus Vsat divided by R plus Vsat divided by R2 divided by R1 plus R2. Or you will be getting, this is substituting this value of R1 and R2 here, you will be getting 28 millivolt is the upper threshold voltage, and lower threshold voltage will be, since this is grounded, lower threshold voltage equal to minus of VUT. For VLT is equal to minus of VUT, because you are grounding this V, or you are grounding this point, or V reference is kept 0. Therefore, this is the upper threshold voltage, you will be getting 28 millivolt, and lower threshold voltage equal to minus, you have to substitute here, V reference equal to 0, then you will be getting it is equal to minus 28 millivolt. There's another problem on again Schmitt trigger. A Schmitt trigger with the upper threshold voltage of 0 voltage and hysteresis with VHSOP of 0.2 volt. Hysteresis width is given. Converts a 1 kilohertz sinusoidal. This is a 1 kilohertz sinusoidal waveform of amplitude. 4 volt peak to peak. This is the 2 volt, and this is the 2 volt. 4 volt peak to peak into a square waveform that is converted. Calculate the time duration of the negative and positive portion of the output. You are asked to find out this duration during the negative, or during, what is this duration, minus Vsat, or this is a ground voltage actually. What is this duration T1, and what is this duration T2, and this is the input voltage, and what is given is the VUT is given as 0, but hysteresis width is given as 0.2 volt. Now we are asked to find out what is T1 and what is T2. That is the problem. This is the input voltage with a peak to peak value of 4 volt. Coming to the solution of this problem, given upper threshold voltage equal to 0 voltage, and the hysteresis voltage is given as 0.2 volt.
hysteresis voltage VH is equal to upper threshold voltage minus lower threshold voltage. Therefore, 0 minus lower threshold voltage is equal to VH. VH is equal to 0.2. And from that one, you can find out what is the lower threshold voltage. Lower threshold voltage is equal to minus 0.2 volt. Therefore, upper threshold voltage equal to 0 volt. Lower threshold voltage equal to minus 0.2 volt. And the hysteresis width for VH is equal to 0.2 volt. So that is determined first. Now you are asked to find out what is this one, meaning that here the upper threshold voltage is equal to say 0 and lower threshold voltage equal to minus 2. For minus 2 means this is, if you see, consider this is the peak voltage is equal to 2 volt and this is equal to minus 2 volt, and here VLT is equal to minus, if it is lower than minus 2 volt, if the input voltage if the input voltage is lower than the reference voltage of minus 0.2 volt, then the output will be changing from minus this, or here it is trans 0 from of course that is changing from 0 to whatever that plus we set. That change transition is taking place this one, and that will be continuing until the input voltage is crossing the VUT. VUT is given as 0. That is why once it is crosses VUT, again that is changing to minus Vsat, or in this case it is written as 0. So ground voltage is written. Therefore, this it is problem it is asked what is the T1 and what is T2. Therefore, in this problem VUT is given, VH is found out, and VLT is equal to minus point. Theta can be calculated, and you can find out what is the theta, and the theta can be calculated as follows. That is, this value is equal to minus 0.2 volt. Therefore, minus 0.2 equal to Vm sine, this magnitude is equal to Vm sine pi plus theta. This is the pi is the angle is theta, pi plus theta, Vm sine pi plus theta, or minus Vm sine theta equal to this minus 2. Vm is equal to 2 actually. Therefore, it is a minus 2 sine theta. Okay, sine theta. That's equal to minus 0.2, or sine theta equal to 0.1, or you can get theta equal to 0.1 radians. This is equal to 0.1 radians. Then you can find out what is the pi plus 0.1 radians is the total on period. This is equal to T1 equal to pi plus. Or if you calculate the total time period, T is given by 1 by F, or 1 by 1000 is equal to 1 milliseconds. The total time period is equal to 1 milliseconds, in which T1 is calculated, and you can calculate what is omega t theta. That is, omega t theta means this one, t theta equal to 2 pi into omega equal to 2 pi f into t theta, which is equal to 0.1, which is equal to 0.1 means this is equal to sine theta equal to, or this is equal to 0.1, and then you can calculate what is this time period, that is from here to this time period, which is equal to 0.016 milliseconds, and this time period equal to t by 2, which is equal to 0.5 millisecond, plus this one which will be 0.516 milliseconds. For the t1 is given by this t by 2 plus this time t theta, which is equal to 0.516 milliseconds, and the remaining period, that is t2, is given by total time period t minus this t1, t minus t1, which is equal to 0.48 milliseconds.